Hello, I'm Richard Van Wyhe with EV4U Custom Conversions. We recently did a video on a $7,500 conversion. A friend of mine has done 2 vehicles and he was able to do the entire conversion for $7,500 each. And we received a lot of interest in that, and so we thought we'd give a little more information on what's entailed in the basic conversion. And so we're going to go over the points that I think you should know, and they are the components, design considerations, and wiring. And we'll discuss each of those topics separately. When we get to the wiring, we'll show you a schematic diagram of the 12-volt circuits, the 120-volt circuit, the safety circuit, so forth. We'll go through all of it and let you see what it takes to design, build, and wire a 120-volt DC conversion that you can do yourself for $7,500. So first off, we'll start with the components. He used an 8-inch motor. It's a series wound DC motor. It's large enough to move the vehicle that we're going to talk about, and that is we recommend that the donor vehicle be under 2,000 pounds. The vehicles that he's used, the Chevy Sprint and the Ford Festiva, both weighed in the 1,700 pound range, which is quite light. I mean, that's the stock factory weight. A comparison would be the Volkswagen Beetle, the classic bug. They were 1,850 pounds from the factory. So we're talking about a light vehicle that is much more aerodynamic than a bug. Bugs have a pretty high coefficient of drag. Not my first choice for a conversion. So we're looking for a lightweight, aerodynamic as possible vehicle. And to power that, we'll use an 8-inch, that's the diameter, DC series wound motor. The other components that you'll need will be an adapter that will replicate the back end of the gasoline engine so that we can mount the electric motor to the bell housing on the transmission. And then we need a coupler that will couple the drive shaft from the electric motor to your input shaft on the transmission. And then a motor mount, or mounts, to mount the motor in place in the engine bay. Then to control the motor, we need a controller, and we recommend a 500 amp, the Curtis 1231C. You can also use a 400 amp for this project, but I recommend the 1231C. And then to cool the controller, you need a heat sink. Curtis recommends a 12-inch by 12-inch by 1/4 inch thick aluminum heat sink. Then you need a pot box, which will feed the signal to the controller. You need a main contactor, which connects and disconnects the battery pack from your controller. And then an emergency and service disconnect switch, which allows you to disconnect the pack for service, storage, and emergency, so forth. So recommend that you have that located where it can be reached either physically or mechanically in an emergency. Then you're going to need a charger to charge your battery pack, and a charge port where you plug the vehicle in, plug the charger in for charging. Wiring, your terminals, the wiring for the high voltage side is double-aught We use a double-aught fine strand welding cable. It is flexible enough and works well for this application. And then we recommend at least 2 gauges, a volt gauge and an amp gauge. Your amp gauge is going to be your efficiency gauge, so you can drive efficiently by watching the amount of current you're drawing while you're driving. You'll notice that you can reach a speed and then back off quite a bit and maintain that speed while drawing less current, which will increase your range. And the volt gauge will be used as your fuel gauge. This is for the $7,500, it's a lead acid conversion using 10 12-volt lead acid flooded batteries. So you could, well, let's move on here. Then there will be relays that we will use for your safety interlocks and for other purposes. Fuses, both for your pack and for your 12-volt accessories. Of course, your batteries, a DC to DC converter, which is used to charge your auxiliary battery, as well as share the load of your 12-volt accessories, windshield wipers, headlights, stereo, all your 12-volt accessories. And that takes your pack voltage of 130 volts and converts it to 13.5 volts. Then miscellaneous items, all your 12-volt wiring and connectors, nuts and bolts, heat shrink, wiring loom or wire ties or whatever the case may be, so you can make your thing look nice. There's just a lot of, you'll need the metal for your battery containment and so forth. And then power brakes. You'll need the vacuum reservoir and a vacuum pump, so forth. And then there's optional items. Depending on where you live, they may or may not be optional, but heater and AC. The $7,500 conversion that he did, the one had air conditioning. The car came with air conditioning originally. He used the output shaft to drive the AC compressor, and I'm not sure if either one of them had a heater. He is from here in Northern California, and he also lived in Arizona, and so neither place gets very cold and not a whole lot of requirement for a heater, especially if you have a 20 to 40 mile range. So let's move on to some design considerations. We've already talked about the donor vehicle. We want a light aerodynamic vehicle that allows us to use the smaller motor, smaller controller, so forth, which keeps the price down. Then we need to think about the component layout. And your biggest user of real estate in your conversion will be your batteries. And so in the battery placement, we want to consider the weight and the volume that these batteries will entail. And so when it comes to the volume, depending on the vehicle that you choose, it's a hatchback or it's a vehicle with a trunk, how big is the engine compartment, and so forth. Those, to a large degree, dictate where you can put batteries. The other thing that needs to be considered is the weight distribution. It's best to keep the weight distribution as close to it was from the factory as possible. And so if all the weight was up front, you want to put most of the weight up front. You don't want to put all the batteries in the back and have a light front end. You'll have handling and braking issues. And so camera quit on me, so we'll start again. So anyway, the weight distribution is important for safety and handling concerns. We want to give that substantial consideration. And then component relationships. It's best to keep certain components close to one another. For instance, the controller and the motor. The shorter the run between the controller and the motor, the better. And then one that comes up a lot, and it's a lot of questions when we do shows and so forth, is the clutch. There are a lot of people that do conversions and do away with the clutch, couple the motor directly to the input shaft. And so there's kind of two schools there. Some say, you know, the clutch isn't necessary, you get rid of weight, so forth. But I'm a clutch fan. I think the clutch is necessary for faster, smoother shifts. It alleviates the wear on your synchros, which you're going to have if you shift without them, because when you're putting pressure trying to slow that electric motor down to the input shaft when you're shifting up especially, the electric motor doesn't wind down as quickly as a internal combustion engine does because of the compression. And so you're going to have to put a little bit of pressure on those synchros every time you shift. Granted, you may not be doing as much shifting with the electric conversions you did with the gasoline equivalent, but I think in the long run you're better off going with the clutch. And then the other reason for the clutch is it's the ultimate safety disconnect. If you have some issue, a worst case scenario, where the thing is putting out full power, I mean, the design you'll see in our wiring has redundancies built in for safety, but the ultimate disconnect is the clutch. And it's just, if you're used to driving a standard transmission vehicle and you're in a panic situation, the brakes and the clutch just go together. I mean, you do it without thinking. And so we'll move on next to the wiring. Like I said, we'll show you the 12-volt circuits and the 120-volt circuits. It's actually 130-volt circuits. Your 10 12-volt batteries actually will put out 130 volts when fully charged. And then your safety circuits, your safety interlocks, that will prevent the car from being able to be driven away while you have it plugged in, prevent the car from taking off when you first turn on the key, that type of thing. So I'll draw the schematics on the board here, and we'll finish up. All right, before we get started with the schematics, let me just say a few things about lead-acid batteries. You must really consider placement of the lead-acid batteries for several reasons. One is they're heavy. Typically, the 12-volt batteries that we're just talking about in this particular kind of conversion, $7,500 conversion, they're going to weigh anywhere from 60 to 66 pounds apiece. So you're looking at a 600 to 792 pound battery pack. That's worthy of consideration for a lot of reasons. One, like we talked about before, the handling and ride of the vehicle, but also in case of an accident. I mean, nobody wants to be involved in a collision, but they happen, and so you need to consider where the batteries are placed, how they're secured, so that in an accident, the driver and passengers are not in jeopardy from a 60-pound projectile. So you want to design it so that preferably the batteries are not within the passenger compartment. And on a conversion on a budget like this, that's a major consideration. On our marketing vehicle, the 1974 VW Beetle, the batteries are within the passenger compartment, and we went through a lot of expense to protect the occupants because of that. The batteries are in a much stronger mounting system. They're located within welded polypropylene boxes and a steel mounting cage system that's designed to withstand a rollover. To do that cost an extra $1,000 or $2,000 to do that. The other thing is when the batteries are being charged, they give off a gas, and the hydrogen gas is explosive. And so if you have them in an area and they're not in a proper box, then you want to make sure they're well vented so that these gases don't build up and cause an explosion. Hydrogen gas rises, it's lighter than air, and so just bear that in mind. On our Bug, for instance, like I said, those are in sealed polypropylene boxes so that in an accident, if a battery did rupture or if a battery exploded while being charged or something, it would stay contained. All the acid is contained within that polypropylene box, which is the same material which the battery cases are made out of themselves. The other thing is that they have a vent system, an automatic vent system that when it's plugged in, fans come on and exhaust the battery boxes. There's also a passive system on there, so when you're driving and so forth, they're vented. But anyway, a lot more hassle and expense than you would typically see on a $7,500 conversion. So that then dictates the type of vehicles that you want to use. The vehicle that we featured on a previous video, the Ford Festiva, he had 4 batteries under the hood, which that's not an issue. Any gases and so forth are allowed to escape to the atmosphere. And in a collision, they're not going to interfere with the driver if you have them properly secured. But then he had 6 batteries in the rear. And so whenever he charges, he has that rear hatch open. And so there's no gases building up in the passenger compartment. They are then dispersed into the atmosphere and don't create an explosion hazard. And also they were located, with the exception of one, they were all located down low, so in a collision those batteries would go down and forward and not come into the passenger compartment. One battery was sitting on top of the others, but that was down low, well secured behind the back seat. Shouldn't go anywhere. So anyway, just wanted to bring that up. Lead acid is not my first choice by any means. We only bring it up because of the price consideration in this particular discussion, and you're not going to get a lithium conversion for $7,500. But if you chose to take this same basic conversion and keep everything on the economical side, with the exception of batteries, you could, you're basically going to almost double the price. 120 volt lithium packs, and it costs you about, depending on where you get them and so forth, 6,000 to 7,000. But they're well worth it in my mind. You have a maintenance-free battery. You got a 10-year life approximately. Just worlds apart. My friend that did the $7,500 conversions, he says he gets a 30 to 40 mile range on the Sprint and the Festiva. And we took a ride here a while back where we went about 32 miles on batteries that are a year and a half old. So he gets about 2 good years out of a battery pack, and then he replaces them. There are 115 amp per hour batteries that he purchases at Walmart, and the pack costs him for 10 of these batteries $900. So quite economical compared to a $6,000 or $7,000 lithium pack. But they have a lot of drawbacks, and weight being a big one. 400 pounds heavier. So anyway, the other thing I wanted to mention before we get into the schematics is to remind you of our 3-day hands-on conversion workshops coming this summer. The first workshop will be towards the end of July. Then we have another one in August, September, and October. And so be sure to check the website, evforyounow.com, for those dates and to register. And if you have any questions regarding the conversions, the workshops, or the stuff we discussed in this video, you can email us at info@evforyounow.com, and we'd be happy to answer any of your questions. I mean, that's one of our main objectives, is to educate the public so that they can do their own conversion. We offer the service to do it for you for those that would rather have a professional do it. We do that. But our main objective, the reason we have the show car and that we travel around thousands of miles every year, is to promote electric vehicles. And by doing the conversions, the design work, the fabrication, and the rest of the stuff that we do helps underwrite the cost of going out and promoting electric vehicles, which gets quite spendy. So anyway, let's move on to the schematic. We'll start with the 12-volt power source, which is your 12-volt auxiliary battery, which is going to be switched through our ignition source. So basically, we'll start and walk through what happens when you turn on the key. And so you get in the car, you turn on the key just like you would in any other vehicle. And we like to install a light, preferably a green light in the dash, so that when you turn on the key, this light comes on to let you know. Camera cut out on me again, sorry about that. Anyway, when you turn on the ignition switch, light comes on in the dash to remind you that the key is on, that the ignition is on. Because there's not going to be any noise, nothing obvious to let you know that the vehicle is indeed turned on. Also, when you turn on the key, that activates, if you have power brakes, that would then activate the vacuum pump relay, which then, depending on your vacuum status, would turn the pump on, or at least have it ready to come on when the vacuum drops. So that's a circuit, and then your light would be another circuit. So then, once the ignition is on, the path is, it comes down here through a safety interlock, and this safety interlock is designed to keep the vehicle from being driven while it's plugged in. And so this goes to your power source, to your charger. So in this case, if you're using a 120 volt or 240 volt, whatever it is, that would be the relay that you would use. So in my little example here, 120 volt AC relay, when it's plugged in, the relay is energized, power from the ignition only goes that far, won't go any further. So you're not going to be able to activate the rest of the circuitry to make the car move. So we unplug the car, it comes through that relay and goes to an inertia switch, which we always recommend. This is in case of an emergency, or not an emergency, but a collision, that would open up. That drops your power to your pot box relay and to your controller and so forth. Just another level of safety. So vehicle hasn't been in a collision, your inertia switch is closed, power comes down, comes over here to this throttle position safety relay. Well, if the throttle is open a little bit, in other words, whatever, the floor mat's holding it open, you've got your foot on it a little bit, and so if that's the case, then this micro switch on the pot box will be open, and the power is going to come here and not going to go any further. Not going to be able to activate our pot box and so forth on down the line. But if that throttle is completely closed, then that allows the power to come through here. It comes through here, activates this relay, and once that relay is closed, then it allows the power to come through. Let's see, where were we? The power comes through, through here, and then it latches it, so that even when you give it the throttle, then this relay stays latched. That's what the first switch is. This is a double pole, double throw relay. Then the other switch here is activated once the throttle is on. It comes through, your 12 volts comes through and goes to your main contactor and activates the main contactor. It also, let's back up here, it comes through here, and yeah, when this is your 12 volt source right here, and when the throttle is engaged, brings power over here to your pot box relay. The pot box relay then, once closed, gives you a signal of your pack voltage to the controller, turning on the controller. It also, and so that power is coming from your pack. So here's your positive end of your battery pack, comes through your main circuit breaker, which is your emergency service disconnect, comes to one side of your main contactor. The contactor is open, that's as far as it goes there, but then it also comes up here and ties to your key switch relay, which is activated when we turn on the key, and that allows power. So when the key is turned on, it allows your pack voltage to go through that relay and to your DC to DC converter, turning it on. So once the DC to DC converter is on, it is now charging your auxiliary battery. So when the ignition is turned off, DC to DC converter drops out, and no more load on your pack from that. So then the other path then from our pack is going over here, your pot box relay, which is activated by the micro switch on your pot box. So when you give it the throttle, this relay closes and energizes your controller. So that's another layer of safety. When you let off the throttle, this relay opens up, takes away power to the controller. So another little tangent here. Once you have the key on and your key switch relay kicks on, you're then going to have voltage going to your DC to DC converter, like I just mentioned. And so that's where you would put your volt gauge that's measuring your pack voltage. This is the negative side back around here to your pack. The positive side came through our main disconnect up here and through. So this is the positive side of that voltmeter and the positive side of your DC to DC converter, and this is the negative side. So then this wire is a wire that comes from the pot box. It's actually encased, and there's two wires that go to the controller. They're not polarity specific or anything. It's just two wires that come to the controller to activate the controller. That's what gives it the throttle signal. So this is your signal input. This is your on input as far as power activation to the controller. So once you give it some throttle, it closes your main contactor. Here's our positive coming up, goes through the contactor to the battery positive of the controller. It also goes to A1 on the motor. And then, so that's one path, and then the return path then goes through your motor, through your shunt, and back to the negative over here on the controller. So that's your high voltage path. Positive side of the pack, through our main circuit breaker, through our main contactor, to the motor, and back to the controller. So now your shunt is going to measure, that's where you hook your amp gauge to it, that's going to measure your current on your pack that's going through your motor. So like I said, that'll be your efficiency gauge. You'll watch that under hard acceleration. You can pull 500 amps if you run the 1231 Curtis 500 amp controller. But typically driving down the road with a under 2,000 pound vehicle that we mentioned, you should be able to drop it down to about 150 amps, depending on the rolling resistance of the vehicle, so forth. But you should, 150 to 200 amps should be your cruising speed or cruising current when you're at speed. So anyway, that's just an overview. A couple other things to maybe note is that depending on how you lay out your pack, between different, if you have part of the pack up front, part of the back, have a fuse between the sections of the pack. If you have a large pack with, say, 6 batteries together, throw a fuse between numbers 3 and 4. That way, in an accident or something, that way if you're in a collision or something, and something gets shorted out, you're dropping out sooner. You're protecting sections of the pack instead of just having one fuse. So anyway, we typically, depending on how many packs, we'll use 2 or 3 fuses. Safety first. And so this is, very simplified overview. My crude drawing. I'm obviously not an artist, not very good at drawing on a dry erase board. But you got to see how everything kind of goes together. Hopefully it shows up on camera well enough. I did it a little small, didn't really draw anything to a very good scale. So we have, like I said, a couple different layers of safety built in, and it's all very simple components. And so if you want to do your own conversion and you want to keep it inexpensive, this kind of gives you an overview of how to do that. There are several good publications out there that spell all this out in print. I'm not going to recommend one over the other. But before you do a conversion, before you get started, do your homework. Research the individual components. Think about the donor vehicle. Think about the big picture. You know, where are you going to put these components? Are they all going to fit in the vehicle? Downside going with a very small vehicle is you have less space to put all these things. So it takes some thought, and in order to have a safe, reliable conversion, you need to give it plenty of thought. So do your homework, and we wish you all the best in your quest for electric transportation. And if you'd like to do a conversion with us, we are offering the 3-day hands-on conversion workshops where we provide all the materials for you. You leave with a nice little binder that has all sorts of information in it covering the conversion. And so the conversion that we do in the workshops is a lithium conversion, but the basics are still the same. Just a little more expensive conversion that we'll be doing. So, and then we're always happy to answer any questions. Feel free to email us with any questions, and we'd be glad to get back to you promptly. And as always, appreciate you watching, and happy EV driving.